Marra da Silva Ribeiro. He's from University of Campinas, and the title of his work is Quantify Spatial Uncertainty and Inferring the Stochastic Wave Attenuation in Periodic Frame Structures. So now we'll have the video, and after we have time for some questions.
Hi, I'm Luis from the University of Campinas, and I'm going to present our study with the title of Quantifying Spatial Uncertainty and Inferring the Stochastic Wave Attenuation. This study has contributions of Vinícius Dalpogiato from the University of Trento, Danilo Belli from the University of São Paulo, Adriano Fabro from the University of Brasília, and José Roberto Arruda from the University of Campinas. As you can see here in the summary, I'm going to present the introduction, then I'm going to present the methodology, the parts related to the parameter estimation and the inference, then I'm going to present how we compute the wave attenuation and how we model the spatial variability. For the results, I'm going to present elements that has homogeneous and spatially varying mechanical properties. Finally, I'm going to present the concluding remarks and acknowledgements. Vibrations can lead to several problems in structural systems, and by using periodic frame structures, we can obtain frequency bands where the waves are attenuated. These periodic structures can be modeled by using the spectral element method and the wave finite element method. However, the variability related to the used manufacturing process can affect considerably the attenuation, and it must be modeled. Assuming that the material property follows a statistical distribution, any statistical estimator can be used to infer the parameters that represent them. In the current study, we use a highly precise Bayesian estimator that uses a combination of the posterior distribution with the estimated wave number of the periodic structure that we inferred via Cronus method. In order to infer the stochastic response, the Bayes factor is used. It gives in practice the ratio of occurring and attenuation against not occurring and attenuation for a given frequency band. In order to compute the wave attenuation, we first model the frame cell using spectral elements, and the dynamic condensation is applied keeping only the external nodes. Thus, the periodic boundary condition can be applied to these external nodes, which yields a polynomial problem that can be solved via companion matrix. For the stochastic analysis, this approach can be combined with the Monte Carlo method, and several samples are analyzed to compute the stochastic response. There are several methods that can be used to model the spatial variability, such as the KL expansion, the EOLE, and the kernel smoothing. All these methods require either an inferred or assumed as known correlation function that relates the spatial variable property, or the correlation matrix estimated from the observations. A common assumption used in modeling such spatial correlated field is a exponential function related to the distance between the positions. Usually, this exponential usually has a correlation length parameter, and as the correlation length increases, the model field converges to the field mean value, as you can see here in these figures. Here in the left, we have a unit cell of the proposed frame structure, and in the bottom we have a frame element composed by 6 of such unit cell. This frame structure will be used in the examples we are going to present for 1 and 3-dimensional variability applications. The simplest way of modeling the mechanical property variability is to assume that the mechanical property of a given frame comes from a statistical distribution, but this mechanical property is homogeneous along the frame element. Thus, using this approach, we have here the first 3 samples of this proposed methodology for the varying Young's models. Then we can go to the 1D spatially varying mechanical property, and assuming different correlation matrices, we can model different types of spatial variabilities. Here in these 2 first figures, as you can see, it varies homogeneously along the frame, and for the two last figures you can see that there are larger mean and variability for regions near the higher parts of the frame beer. Using the first approach, as you can see here in the three first samples, the mechanical property, the Young's modulus, varies homogeneously along the frame element. And here we use the base factor to infer the stochastic response as attenuations for longitudinal flexural and torsional waves for the homoscedastic Young's modulus spatial variability. And as you can see, there are some intersections of these three types of waves for the attenuation. Thus, using the second approach, as you can see here, the three first examples, where the Young's modulus varies in a heteroscedastic way, and using again the base factor to infer the stochastic attenuation response for longitudinal flexural and torsional waves, there are some intersections here when considering the attenuations. In order to validate the computed attenuation response, we also performed some experiments on the longitudinal and flexural force response, and as you can see, the model can capture considerably the response for the flexural wave and also for the longitudinal wave. The same procedure can be used to model a 2D spatially varying mechanical properties, where, for example, plates with spatially varying mechanical properties can be simulated using a two-dimensional spatial distribution and the kernel smoothing. The same procedure can be applied according to a three-dimensional spatially distributed mechanical property, and without applying the kernel smoothing, as you can see here, two very near positions can present very different values of the Young's modulus. And after applying the kernel smoother, it becomes smoother, and two near positions have no more such different values of the Young's modulus. In addition, for this proposed three-dimensional spatially varying mechanical property, we assume a distribution that tends to be higher values in the higher positions of the web here than it has in the center of the web. For the concluding remarks, in this study we present some techniques for modeling 1, 2, and 3-dimensional stochastic variability throughout structures. These methodologies can be applied to frame or plate structures to model their mechanical properties spatial variability for different assumptions and using different spatial correlations. It is also shown that these representations may be used to predict robust attenuation bands in quasi-periodic structures. The authors gratefully acknowledge the financial support of the FAPESP and CNPq for these process numbers here, and thank you.
We have the video, and now we have time for questions. I have a question for you, please. So, thank you for the presentation. And do you model the Young models as a Gaussian stochastic process along the whole length of the structure, or do you use, which stochastic process do you use? You talked about the variables, you use Gaussian variables, but you use the stochastic process.
Yes, actually, for this case we assume that for each position in the frame element, it follows a Gaussian distribution, a normal distribution, actually a multi-variable Gaussian distribution, but it is not it is not a necessity. We can assume any distribution for each position. We can assume any distribution actually. For a study that we made, we assume a gamma distribution, because if we assume a normal distribution, we may have, even if it is related to a very small probability, we may have negative values for the Young's models. So in this case, we made this mistake, but in other studies, we assume a gamma distribution that we inferred using a Bayesian estimator, where we also used the Pronis method to include more information about the distribution that we are trying to infer. So in this case, we made this mistake, but just for the sake of simplicity, because in other studies we assumed a gamma distribution, and it is not a problem. You can adapt to any distribution you want, especially when you're using the AOLE, or a combination of sampling and applying the kernel smoother.
Okay, so, thank you.
Thank you for...
Now we have a question from Thiago Rito, and he's thank you for your nice presentation, and he's asking you to talk more about Bayes factor and its using your problem.
Yeah, that's a nice question. Thank you, Professor Thiago Rito, for the question. And we decided to use the Bayes factor to infer on the stochastic response, because in the first study that we published, we proposed a Bayesian estimator to infer on the distribution of a given mechanical property distribution. And by doing that, we thought it to be more reasonable to also use a Bayesian inference, because we used a Bayesian estimator to infer on the mechanical property distribution. So we also used a Bayesian inference on the stochastic response, and it gives a ratio of chance of occurring against not occurring, a band gap, and it is a straightforward approach for those that are not accustomed with the statistical approach. So that's why we decided to use, and we kept using for the other results.
So thank you. And I have one more very quick question. Why do you interested in this specific form of structure? Any special reason?
Yeah, it's because firstly we were planning to apply to a plate made of a composite, but when we start to study the frame elements, when we apply the block flow periodic conditions, we start to see that there are some points that we could study deeper. And this approach, when we make the polynomial problem using the spectral element method, we saw that there are some gaps that we could study that it does not occur for the plate structure. So we just try to apply for a structure, and we start to see that there are some gaps, and we try to study deeper. That's
Okay.
It was not planned first, but we then saw that there are some interesting points that we could study.
So thank you again, Luis Henrique. And now we're going to the second presentation. Is Thiago Fernandes. He's here, and he's from Federal University of Santa Catarina. The title of his work is Bayesian Probabilistic Approach for railway bridge model updating. And now we'll have his video.
Hello everyone, I'm Thiago Moreno Fernandes at Federal University of Santa Catarina in Brazil. And in this work, me and my advisor, Rafael Holdorf Lopes, apply Bayesian probabilistic approach for rail bridge model update. So in structural engineering, there are many cases which design data is insufficient or non-existent. In this case, there is a demand to assess the behavior of this structure, usually simulated by numerical models. So the main idea of the model updating is estimate uncanny parameters based on experimental data. There are some methods for solving model updating, such as optimization methods or Bayesian methods. The Bayesian inference summarizes the degree of information regarding of the parameters of interest through the probability distribution. In this case, the combination of a prior knowledge with the probability of experimental observations allows to obtain a posterior probability distribution that reflects on the estimation of the parameters of interest. In this case, this is the posterior distribution, this is the prior distribution, and this is the likelihood distribution. Bayesian inference provides to estimate the error between the experimental and numerical measurements. In this case, the error can be simulated by a normal distribution with a zero mean and a standard deviation that will be estimated. There are some techniques for sample the posterior distribution, such as Monte Carlo with Markov chain. The MC build a Markov chain over the space of the parameter of interest in order to build the posterior probability distribution. So in this case, a sequence of random parameter is called a Markov chain in a space for every measurable set if the distribution for the next point depends only on the current state of the chain. One important algorithm based on MCMC is the Metropolis-Hastings, which is executed by independent probability distribution for each of the parameters. So the first step is to initialize the sample value for each random parameter, usually from the prior distribution. So the proposal parameter will be generated by a perturbation of the current state. And for the next step, we compute the acceptance probability based on the distribution of the proposal parameter and the current state of the parameter. So we draw a random number uniformly between 0 and 1, and if this value is smaller than alpha, we accept the proposal, otherwise we reject it. So this process is repeated until the defined sample size. As case study, we selected Canelas Rail Bridge, which is located in Portugal. The bridge consisting of 6 simply supported spans with 12 meters each. The structure is composed of a reinforced concrete slab deck, ballast, concrete sleeper, and rail. And main studies evaluate the suitability of the structure to increase the speed of trains. So in this case, situ tests was developed in order to assess the dynamic responses of the structure. So the first vertical bend mode and the first torsional mode was estimated. That will be applied in this work. So in this work, the main idea is estimate 2 physical parameters of the structure, vertical stiffness of the supports, and modulus of the angle of the concrete. And as mentioned, The Bayesian inference provides to estimate the standard deviation of measurement errors. That's the idea of this work too. For the model updating, one numerical model was developed, and it was discretized with approximately 3,300 elements with these exact values that will be estimated. For the model updating, a total number of 100 experimental responses is simulated based on a perturbation of 4% of the exact value of the stiffness parameters. For the mean and standard deviation of the prior of the stiffness parameters, the values are fixed with a mean around the central value of the design boundaries of these parameters, and with a standard deviation of approximately 10% of the prior mean. The mean and standard deviation of the prior parameters related to the measurement errors are set in a very informative way, since the prior mean is given by the standard deviation of a simulated experimental data, and the prior deviation of 10% of the prior mean. The perturbation of the Metropolis algorithm of the parameters of stiffness is given by the Gaussian distribution with a zero mean and a standard deviation or random walk of 1% of the exact value of the parameter of interest. Refer to parameters of errors. It's applied the standard deviation of 10% of the standard deviation of simulated experimental measurements. So we cannot that all probability distribution follow a Gaussian. As a result, by the tracy plot, we cannot that all parameters reach the stationarity. And by the histogram, we cannot that all parameters follows a Gaussian distribution with a higher density close to the exact value for each parameters of interest. As the final remarks, the Bayesian probabilistic approach shown satisfactory for this problem. All of the parameters of interest were estimated with a good accuracy. On the other hand, the incorrect choice of input variables required to the Metropolis-Hastings algorithm can make the solution of poor quality and imply the non-stationarity of the parameters of interest. Thank you so much.
So thank you to your speak. And now we have some questions. I have a question for you. And you said that you used the first two natural frequencies of torsion in the model updating. So how do you use it? Can you talk a little bit more about it?
Sorry, I don't understand this question. Can you repeat, please?
Yes, of course. You said that you use the first two modes in the model updating. How do you consider these two natural frequencies in the model updating? How do you make this consideration?
Okay. In the Bayesian inference, there is the likelihood distribution that will be provided the experimental measurements for the model update. So in this case, these two values of the natural frequencies was applied but in other cases, usually apply the displacement of the structure, or such as deflection. But in other studies, these two modes of the vibration of the structure was estimated, so I apply these values for the model update in the likelihood distribution.
Okay, so thank you. Now we have a question from Professor Adriano Fabro, and he's asking you, how do you consider seasonal changes on a structure?
Sorry, signal.
No, seasonal.
Seasonal change. Okay.
Do you consider that
case,
just
I simulated?
No, so you can. Okay, you can stop.
Seasonal cases regarding of the parameters of interest, or the values of the responses of the structure. In this case, the natural frequencies of the modes of vibration. In this case, it was
yes.
In this case was modeled the disturbance of the experimental results. So in this case, it was modeled as a perturbation of 4% of the exact value of the natural frequencies, in order to simulate the differences between 100 values of measurements. So in this case, there is a disturbance of the responses of the structure to simulate the experimental tests. But
Okay.
the values of the parameters of interest was not considered with the perturbance, but there are some methods, other methods in Bayesian inferences that in order to estimate the standard deviation of the values of these parameters of interest, in order to add the information of the standard deviation of the measurements. So in the hierarchical Bayesian inferences, can be estimated the standard deviation of the parameters of interest. So in this work, I estimate the standard deviation of the errors between the numerical and experimental measurements, and to the estimation of the physical parameters of interest.
So, okay, thank you. And the last quick question that I have for you is that you said, how long it takes to make the numerical simulations? Is it very time consuming, or is it quick, even using just one half span of the bridge?
The numerical model was modeled with the one span of the bridge. The bridge is consisting of 6 spans, but the numerical model for the model updating using the Bayesian inference required a high number of samples. In this case, the number of samples was 10,000. So for the numerical model was simplified with the one span was required 10 hours approximately for the simulation. So if it was modeled with a 6 spans, there is required a high computational cost in order to 6 times.
So yes, it's very time consuming. So thank you for your answers, Thiago. And now we are going to the third presentation of the session, which is Vinícius Matoso Reis da Silva. He's from PUC-Rio, and the title of his work is Reservoir Characterization, Comparing Different Ensembles Methods. And now we have his video.
Hello everyone, my name is Vinícius Matoso, and I present the work developed by me, Dr. Demir Maza, Professor Abelado, and Márcio Carvalho. This work is called the Reservoir Characterization Comparing Different Ensemble Methods. This work is a part of my master thesis. This work is inside of the reservoir management area, and more specific, inside of the reservoir characterization. In a summary way, a reservoir characterization means to estimate the different properties from the reservoir, such as the different permeability values and regions. To make possible the characterization, some data is necessary. To obtain this data, the well tests are commonly made. This test consists in the controlling process of opening the production valve during the period called the drawdown, followed by a static period called the build-up. During the whole test, the pressure and temperature data are registered. Despite we have good resolutions for pressure and temperature data, commonly only pressure data are used to make this reservoir characterization. The problem consists of estimating the permeability of the reservoir based on data. For this, we create a simulated data with non-permeability values, and then we use an optimization method to make their history match and estimate the values for its permeability. So, in order to estimate a range of value as response, we use an ensemble of simulated model and use an ensemble-based method to make the history match and achieve a range of values as a response for each parameter. The main goal of this work is to compare the reservoir characterization using the genetic algorithm, the ensemble-smoother, and the ensemble-smoother with multiple data simulation method. To achieve this objective, we implement the ensemble-smoother and the ensemble-smoother with multiple data simulation method, and then we evaluate the computational cost and the parameter estimation for each method. An isothermal well reservoir simulator was used to build a set of simulated data. The LLMP group from PUC-Rio developed this numerical simulator using the finite difference method. It consists of a well-born couple with a 1D cylindrical reservoir for a single-phase fluid flow. The observed data was captured from the sand phase, that is the connection region between the well-born and the reservoir. And to simulate the measurement data was add a normal distribution into the simulated data. In this work was used the ensemble-smoother that make a single global update and the ensemble-smoother with multiple data simulation that make many global updates. The update formula are similar less than alpha E, that is the inflection factor that obeys this formation rule. The CMD and CDD from both methods are generated in this way. The CD is the covariance matrix of observed data measurement error, and the Duke and the EOBAS is the observed data, and the D is the calculated or simulated data. The CD matrix used comprised of two diagonal blocks associated with each independent observed data. The first block corresponds to the pressure data, followed by the temperature data. The CD matrix used was created based on a SUI PhD thesis that used the Joule-Thomson coefficient to correlate the pressure and the temperature data into the Levenberg-Marquardt method. The CD matrix also has an addition of a weight of 10 power less 4, and to avoid scale problems, the pressure and the temperature data was normalized. The genetic algorithm is also an optimization method, and the population here is the ensemble of the vector of parameter. Each vector is a chromosome and each parameter is a gene. The operator of this method is the mutation that randomly change the value of one gene, and a crossover that make the combination of two chromosomes into new chromosomes. The fitness function used was the quadratic error between the observed data and the calculated data divided by the calculated data. This fitness function was used to avoid scale problems, and the optimization toolbox from MathWorks was used because it has this genetic algorithm implemented, and the crossover fraction was set 80% with the good results. The reservoir configuration analyzed was a homogeneous and single porosity cylindrical 1D reservoir. The observed data was captured considering 2 days of flow at a constant rate of 800 meters cubes per day, and the fluid properties and rock properties were extracted from Galvon works. Instead of sorting the permeability value, we used the log transformation to reduce the amplitude of the permeability values and give the Gaussian format that is required for the Sembos-Mutter and the Sembos-Mutter with multiple data simulations. So we use a normal distribution with mean 5 and a standard deviation of 1 to generate the log permeability for the Sembos-Mutter and the Sembos-Mutter with multiple data simulation. And for the genetic algorithm, we set a limit of 2.0 to 7.5. And for the porosity, was used a normal distribution with mean 0.2 and standard deviation of 0.05 for the Sembos-Mutter and the Sembos-Mutter with multiple data simulation, and for the genetic algorithm were set the limit of 0.03 to 0.3. So the configuration analyzed were the Sembos-Mutter and the Sembos-Mutter with multiple data simulations, considering coupled data, and for the genetic algorithm were set in pairs, one considering the coupled data and the other considering only pressure data, using 4 generations, 16 generations, and 20 generations. Let's pass to the results. And considering 4 simulations from the SMDA and 4 generations from the genetic algorithm, the SMDA provided an accurate result, and the Sembos-Mutter with just a single update provided a better estimation than the genetic algorithm considering 4 generations. Increasing to 16 generations, the genetic algorithm with both observed data provides a better estimation than using only a single assimilation from the Sembos-Mutter. And increasing to 20 generations, the genetic algorithm provides a simulation similar to the Sembos-Mutter with multiple data simulation, and the use of combined data in black provided a better estimation of the porosity than using the single pressure data in red. So, as conclusion of this work, we have successfully implemented the Sembos-Mutter with multiple data simulation and the Sembos-Mutter method. Coupled pressure and temperature data can be used to estimate the reservoir parameters. The Sembos-Mutter provides a better estimation than the genetic algorithm with 4 generations, and to estimate similar values, the GA needs to pass the ensemble 16 times more than Sembos-Mutter with multiple data simulations. And as future works, we want to provide randomly initial guess to genetic algorithm and run many times with the same number of generations to evaluate the impact of the observed data. And we want to increase the number of parameters associated with the reservoir characterization. Finally, we'd like to say thank you for the attention, and I'd like to say thank you for those institutions for the financial supports.
So, thank you for the presentation, Vinicius. I have a question for you. You said that you add Gaussian noises to the observed data, I mean pressure and temperature. Do you consider them to be independent, to have the same, I suppose, independence, but they have the same variance, or do you use different variants for each one of them?
No, it was used different variants for each them because the gauge that capture the temperature data is different from the gauge that capture the pressure data. So we search in the literature these possible values from these noises cases from these measurement gauges, and we put different noise for each data. And we also compare, but not shown in this work, to add into the pressure data and harmonic noise in order to evaluate, for example, the tidal effects. So we also made this configuration, but was not shown in this work.
Okay, so thank you. Now we have a question from Américo da Cunha, and he's asking you that your fitting function doesn't use regularizations. Don't you have convergence problems? How can you ensure the best fitting solution in this case?
Okay, we know the best fit solution because it's a synthetic data. So we first make these synthetic data so we have the permeability and porosity value that we are expecting to achieve. And after we add this noise and to try to create a real data or real close to real data, so we can have more evidence of where we're supposed to achieve because of this synthetic process. But getting a real data, we not have this true results to make this comparison.
So thank you. Now we have a question from Professor Thiago Rito. And he's asking you if he understood correctly, you're using randomness for the deterministic optimization problem. And in the future, do you intend to consider parameter uncertainties, which will lead to stochastic optimization problem?
Yes, in future, we're now looking for increasing this reservoir configuration. So we are looking for different methods. For example, the genetic algorithm is a little bit expensive because we need to rerun the simulator, the flow simulator many times. So we need to use a method that we don't need to restart the flow simulator. That is the expensive part of the process. So we are searching for method that reduce this time that we rerun the simulator. So any process could be used in this case.
Okay, so now we have one more question from Américo da Cunha, and he's telling that the generic algorithm is slow and your problem is expensive. And do you know the cross-entropy method? He believes that it can be more efficient for your problem.
I thank for this question because I don't know this method, and I will take note to start to looking for it because it's real a problem, this expensive part. So any method that could gain into this flow simulator rerun, as I said before, is a new case study that I will be pleasure to study more about it.
Okay, what is the computational cost of your simulations?
Okay, into the directive problem for simulate 2 days or 4 days of flow is less than an hour, for example. But to make the whole estimation process, my sample size is 100 because the SMDA, the literature people use this value. So I create a population with also 100 individuals, and the whole process for the genetic algorithm take more than 1 day, and for the SMDA is less than 1 day. And how the process we need to give a quickly answer. For example, we are making the test for 4 days. You can even spend 5 days to make an estimation. So we need to make quick this estimation.
So thank you, Vinicius, for the presentations, for your answers. And now we're going to the fourth presentation. The speaker is Lara Werneck Vieira, and she's from University of Rio Grande do Sul. And the title of the work is Verifying Explainability of Scene Generator Efficiency Prediction with Shape Value Interpretation. So now we have the video.
Hello, my name is Lara. I'm a PhD student of Federal University of Rio Grande do Sul, and I'm here to present my paper entitled verifying explainability of steam generator efficiency prediction with Shepp value interpretation. The main topics of this presentation are my personal presentation and introduction, methodology, results and discussion, and conclusion. So my personal presentation, I'm a PhD student, as I have said before, at Federal University of Rio Grande do Sul. I'm a Master of Science in Mechanical Engineering, finished in 2020, and I'm an Energy Engineering from Federal University of Santa Catarina. My interests are thermal systems, energy, multi-fidelity models, and machine learning. And here you can see my contact. So, introduction. This paper was developed based on Pecém Power Plant, a coal-fired power plant located in Ceará, north of Brazil, which accounts with 3 units of 360 megawatts. The model was focused on the steam generator, and to start this conversation, I want to talk a little about explainable artificial intelligence. Here we can see a robot, which is not the topic of this paper, but just to have your attention and talk a little about it. When we talk about explainable artificial intelligence, we have 3 main points that I want to discuss. I think it's good to think about it. That is trust building, human curiosity and learning, and finally detect biases. So our modeling approach is explainable AI techniques to interpret the steam generator efficiency prediction based on machine learning method. And why we want to study it? Because the machine learning model prediction is more reliable if the model can explain why it made the prediction, and also help its user to develop a better understanding and intuition on the prediction problem. So here we have a trade-off between accuracy and the interpretability of the model, which reflect the ability to correctly interpret a prediction model's output. So, considering our case study in this paper, which is the steam generator of Pecém Power Plant, we have a lot of available data, which allows us to develop a complex model, but we have to analyze because sometimes simple models may be preferred for easy interpretation. So what I want to discuss in here is we have a complex model and you want to know how important is each feature of this model and how we can make this interpretability. So our model is focused on the steam generator, and why the steam generator, just talk briefly about it because the main idea here is it's the core of the power plant and the component with the highest potential of improvement. That's why we are studying the steam generator. So our methodology, we started with data analysis, with data collection and data processing. Second step, machine learning model, which we use artificial neural networks. And finally, third step, model interpretability with Shepp approach and parameter contribution. And the results and discussions of this paper, so the input parameters were selected based on their controllability. Why that? Because you want to help the operator to manage the maneuvers of the power plant, so it's important to have this controllability about each of these input parameters of the model. So we had a lot of options and we chose between all the available parameters those ones who the operator can have some influence. So we have the primary airflow, pulverized coal outlet temperature, speed of the dynamic classifier, secondary airflow excess of 2, secondary and primary air pressure, and as the output steam generator efficiency. We worked with acquired data from the distributed control system, which were acquired from half an hour mean values. The data set was analyzed and processed to remove gross errors and outliers. And we also had a filter by electric power generation to reflect the base load of the power plant, which works in the range of 340 to 365 megawatts. Here is the selected ANN. We have 300 layers with 8 neurons per layer. Here we have our 7 input parameters and 1 output, that is a steam generator efficiency. And what we want to know is we have ANNN, which is capable to predict the steam generator efficiency based on our historical data. But we want to know feature importance and parameters contribution. So if I ask you which is more important to steam generator efficiency, secondary air pressure or primary airflow, that's what you want to know. And to have those answers, we use SHAP approach. SHAP is Shapley additive explanation, which is a game theoretic approach to explain the output of any machine learning model. And here we have the average marginal contribution of a feature value across all possible coalitions. Here is one of our responses. So we'll have the feature importance and the respective contribution or impact of each of the 7 variables, input variables on the model output. So we can see here our 7 input parameters. The most important one is the first parameter, which is primary airflow. And this is interesting to analyze because we have in here the greater the distribution of points along the SHAP value axis, the greater the impact of the feature on the output. So that's why we have the most important feature as the primary airflow, followed by primary air pressure, which is the 7 parameter, and then pulverized cold outlet temperature, and then the less important one is the parameter 5. And we can also analyze the impact of each feature in the output for 2 arbitrary conditions that I have here in the next 2 figures. And the red features are helping to raise the chance of increasing the steam generator efficiency, while the negative features are lowering the chance. So we have two main contributions to increase steam generator efficiency, which were given by parameter 1. And as we have seen before, this is the most important parameter. So here we have a specific condition of 0.82 as a steam generator efficiency, or 82%, and here the second case is 85%. So how we have this steam generator efficiency with these contributions of each of those parameters. And so the conclusions of this paper, we had applied artificial neural networks models to predict the steam generator efficiency of a coal-fired power plant. So we are capable of doing that. The model was based on acquired data from pacing power plant. And finally, the application of SHAP allowed to identify the impact of each input feature on model output. Why this is important? Well, first, because the identification of feature importance is essential to validation of model reliability, and because operators of the power plant can concentrate their efforts to control the really impacting variables. Thank you for your attention.
Using neural networks and you're using 3 layers in your simulations. So why 3? Didn't try different numbers of layers?
Good morning. Yes, we tried actually to decide between different architectures of neural networks. We tried different ones with different number of hidden layers, different number of neurons. And at the end, we chose the best neural network with the simplest architecture.
So, thank you. And when you're doing the analysis with the SHAP graphics, you consider that if a parameter has a wider variability, it has a greater impact in the results. But how do you compare the different variances or variability from different parameters?
Yes, actually, we are working with a predefined range of each parameter. So considering we have this range, that is the operational range that the operators working during their daily life. So we have this range, and within this range, which parameter have the greatest contribution on the output? That's the main point of the analysis. And it's important because we are analyzing, of course, variance, but we still, if you see the graphic of the SHAP value interpretation, which red and blue colors, it's important to notice that when we have the difference between the red and the blue colors, we have an impact, but if the colors are mixed in the graphic, it means that maybe that parameter is not so important because the impact on the output is varying even for lower or smaller range of for the lower or the higher range of the parameter. So that's the analysis.
So thank you for your question, for your answer. Now we have a question from Américo da Cunha, and he's asking you he thank you for your presentation, and he asking if you can comment about how game theoretic approach can increase the insights about the system of interest and how they compare with other approaches based on physics paradigm.
Okay. This SHAP game theoretic approach is more applied on machine learning models. That's why we are using that. We have another papers, if you are interested, that we use design of experiments, for example, to analyze the impact of each parameter on the output, which we apply in physical models like mass and balance models, mass and energy balance models, and not necessarily in machine learning models. So in this paper, we decided, okay, we are now working not with physical models, but with machine learning. So what can we do to analyze with an approach that is dedicated for this kind of modeling? That's the reason why we try to use SHAP value interpretation. That's the main point of the analysis. And we could compare the results. Is that the answer you were expecting or not? I can comment more, but...
Okay, so thank you for your presentation. Now we finish this part of the session and we come back at 9:45. So thank you for all that are watching us, and okay.
All right, who has already presented and want to leave the session, now is the moment for you to start just watching it on the Coben site.
the video, it's me that I need to put the video, or the organization of the Congress?
Sorry, that there was a small delay, and we will start again.
Hello everyone, I am Augusto Delval Marques, and this presentation concern the work steam generator efficiency simulation with a multi-fidelity approach. Here the content of this presentation. I would like to start with a brief personal presentation, after that introduction of this work, followed by the methodology, results and discussion, and finally some topics for future work. So I am a master's student at Promec URGS and mechanical engineer from the same university. My main topics of interest are thermal system, energy, multi-fidelity models, and machine learning. Please feel free to contact me to discuss by email to discuss any of these topics. So the introduction of this work is focused on the steam generator of the Pecém power plant. Pecém is a subcritical coal-fired power plant with 3 units of 360 megawatts each one. And here I would like to bring a discussion about two methodologies of built models, the machine learning based methods and physical equation based models. And here I bring some limitations that I see in each case. So for the machine learning case, normally we require a lot of data, and this method has poor extrapolations, and we are completely dependent of the quality of the data. And the other side, in the physical equations models, they require many simplifications, otherwise it can be really difficult to solve, and normally they don't are sensible to equipment particularities, like different points of operations or equipment degradation. And with that, this is the main question of this work. How can we leverage information from different models to get an answer? So to answer this question, we can combine the data-driven models with physical equation models to build a multi-fidelity model. And what is a multi-fidelity model? So the purpose of multi-fidelity is to use different levels of information to build new models where each source of information has a different fidelity level. So we can have, for example, a simulation 1, simulation 2, simulation 3, each one with a different complexity. And also we have the real world. By real world, I mean a real experiment or real measures of equipment, and we can combine all of this source of information to build a multi-fidelity model and leverage each source of information. So the high fidelity is a function or experiment or even a model that is expensive and to run. So because that we don't have enough information to build a surrogate model based only on this source of information, but we can use another low fidelity model that is more simple and cheap to run a lot of simulation and fill the space project. And combining these different sources of information, we can build a multi-fidelity model. Here it's assumed that both fidelities can be modeled as a Gaussian process. A Gaussian process is a random process F where any field set is a multivariate normal. So in this picture, we can see a collection of random function, and if we do a marginalization at any point, we have a normal distribution. So what's the idea behind the multi-fidelity? The idea is that our expensive function can be represent equal the cheap function plus the difference between the expensive and cheap function. And if we replace each of these functions by a Gaussian process, we arrive in this equation shown here. And because we are using a Gaussian process, the sum of two Gaussian processes is still a Gaussian process. So we can bring information of each n source of information to build a new Gaussian process that better represents our problem. So here we have the surrogate of the expensive function, the surrogate of the cheap function, and the surrogate for the difference between the cheap and expensive function. Now the methodology applying this work. We start with a mass balance model. To explore the mass balance model, we use the experimental design. As a result, we have a matrix of inputs and outputs of the balance model. In the other side, we use measures data points. Combining these two sources of information, you build the multi-fidelity model. And finally, this multi-fidelity model was compared with the mass balance model alone. So here is a picture of the mass balance model. He has 149 components and 6 inputs parameters. The primary are mass flow rate, the pulverized cold temperature outlet, the stoichiometry, O2 excess, the secondary air pressure, and the primary air pressure. And the only output of interest is the steam generation efficiency. To explore the model, the latent hypercube design with 131 experiments was used to fuel the space project. In the other side, as a high fidelity source, we used these 11 experiments that were performed by Vieira in 2020 in the real equipment. And here the parameters P1 until P7 are the same used in the mass balance model. So combining these two sources of information, we can build the multi-fidelity model. And now the results on discussions of this work. Here in green are the results of the mass balance model alone performed in the 11 points measured by Vieira, and the points close to the diagonal line are the results that are close to the values of efficiency of the real equipment. And here in red we have the result for the same inputs run in the multi-fidelity model. As you can see, for our case, the multi-fidelity model was able to achieve a better result than the mass balance model alone. To build this figure, in each case, the corresponding input points was left out of the covariance matrix of the Gaussian process, so the results are unbiased. As a conclusion, we can say that the multi-fidelity was able to build a better representation of the equipment than the original only based model. And also the methodology was able to use a different source of information to build a new function that better represents the steam generator. So some topics for future work are explore different parameters combinations, to quantify a low and high fidelity information necessity, build models with multi-outputs, and also use more than one simulator to build a multi-fidelity model. Thank you very much for your attention. Bye.
So we may start. We have a first question from the chat. It was made by Professor Américo. So Augusto, the question is, for a proper use of multi-fidelity models, the surrogate must pass a rigorous validation process. Can you comment how do you validate the surrogate?
Hello, good morning. Thank you for the question. So by surrogate, you mean the mass balance model? If yes, it's a commercial software that I use to build the distinct generator model, and it was validated against the measured data of the real power plant. I don't know if this answered the question. If no, I can complement.
Maybe in your paper you have some measures of how well the new model fits how well the surrogate, like a percentage of error. How did you calculate this percentage? It was with respect to the actual data, or
yes?
Okay.
Yes.
And just a question from me. How did you maximize? How would you optimize the Gaussian the likelihood necessary to obtain the Gaussian process parameters?
Yes, it was a likelihood maximization. It was by the maximization of the gradient of likelihood.
Okay, so you use the gradient-based algorithm for this purpose. Okay. Any other questions from the?
No more questions in the chat.
Okay.
Okay. Thank you.
So we thank you, and we thank you for your presentation and answers, Augusto.
Thank you.
Hi, my name is André César Martins de Miranda, and I'll be presenting this paper called Engineering Reliability Applied to a Line of Packing Machines. This was made with my colleagues Lidiane de Paula Pinto Mapa from the Federal University of Minas Gerais and Arthur Helek Ladeira from the Federal University of Ouro Preto. So we are going to be talking about reliability engineering, which is a technique that allows us to monitor the performance of equipment, systems, components, and it also allows us to map the frequency and the characteristic types of failures and make some probabilistic failure handlings. As a result of this, we can obtain the lifetime prediction of a component of equipment. It also facilitates the uncertainty analysis and decision making. And so from that, we can obtain a good functional performance of the equipment. So to do that, we have to see some concepts. First, we're going to be talking about the failure density function, which is a function that conceives the variation of the failure probability per unit of time. So here we have the formula of this function, and it's a derivation of the cumulative failure function that shows the probability of failure of a unit between a period of time from T1 to T2. And we also have the reliability function represented by the letter C, and it's the probability of survival of an item in an established interval, which could be a time, number of cycles, or distance. And it represents that between that interval, we won't have the failure of the component. So here we have the formula, and we can see that it's based on the integral of this equation. And we also have the rainbow distribution, which is a model widely used for failure time analysis. It's recommended for equipment with components in line, especially equipment with electronic components. And it's a flexible model that allows us to assume forms of normal distribution, which has an increasing failure rate, exponential distribution with a constant rate, or distribution with a decreasing rate. So here we have the formula of the rainbow distribution. And as we can see, we have some parameters here, like beta, which is the non-dimensional shape parameter, and modifies the shape of the probability density function, which can represent infant mortality, maturity, or senile mortality, depending on the value of beta. We also have this factor eta, which is the scale parameter, and refers to the life of a component, outlining and simulating a distance, time of cycles elapsed from the beginning of the activity to the failure, and also the parameter gamma, which we call location parameter, and it represents the initial life of a component. So if we have a component that's new, we should consider this parameter as 0. By adopting some mathematical manipulation and using logarithmic scale, we can obtain this formula, which is a formula of a linear equation. And by this formula, we can apply some graphical tools and linear regression, and we can obtain these parameters. And by these parameters, we can obtain those factors that we have seen, like beta and eta, as we are going to see in this paper. Another tool that I'd like to point is the failure tree analysis. And it's a deductive technique. It uses some Boolean logic to analyze the combination of failures, and it allows us to see the sequence of these failures. Normally, it's based on some sort of code. And so in here, we are going to be using the FTA based on the ABNT 31010 from 2012. So about the method of this work, we have made a study of a food industry case of a packaging line with 15 machines. These packaging machines work with products in the form of powder. And the capacity of this equipment is from 10 grams to 150 grams. The data was collected in this month, January from 2019, and we have used the software Excel version 2016 to make the analysis. So here we have a flow chart. So we have made the data acquisition, the pre-analysis of the data, the equipment analysis. From the equipment analysis, we have selected one equipment to make the study of reliability, and the failure tree analysis of the critical parts. So here we have a graph showing the time spent in maintenance in each one of the 15 equipments. So we can see that the machine number 1 has the higher number of hours of maintenance, which represent from the total 14%. This was based in 743 events of maintenance in the 15 machines. So since the machine number 1 is the more representative, we have made the study on this equipment. So here we have the rainbow distribution plot. So, and as we have seen before, it was made a linear regression in which we had obtained this formula. And by this formula, we have made some mathematical manipulation to obtain the eta, which in this case was 330 minutes, and the beta parameter, which is 0.86. We can see here that the reliability of this regression is very high, 95%, almost 96. After that, we have made this graph of the reliability of the machine, in which we can see a behavior very premature failure, since this curve is exponential now, And for instance, after 20 minutes of operation, we have a reliability of only 50%. We can also see this behavior here in this cumulative failure graph from an interval from 0 to 2000 minutes. After 200 minutes, we can see that the cumulative failure is it's a little bit higher than 50%, which is a very premature failure behavior. So based on that, we have made this graph, this Pareto's graph of each one of the causes of these failures on the equipment. And if we consider the four main causes here, we are talking about 69% of the causes. So due to that, we have applied these four causes in the failure tree analysis over here. And when we take a look at the main causes, we have seen that the root cause of these failures are related to the end of life of the parts, some failure on the procedure, some operational error, and also non-compliance on the package. So I would like to thank you all for watching this video, and I'll be happy to answer any question you might have. Thank you.
Before starting the questions, let's introduce who gave the talk. So the talk was given by André Miranda from the Federal University of Minas Gerais. So is there any questions from the chat or the other participants? Okay, I have a question. The choice of the Weibull distribution, could you talk a little bit more on that?
Yes, the Weibull distribution is commonly used for analysis of reliability in maintenance. That's why we have chosen this distribution, and we saw that it's very it's quite good for this application. Okay.
Okay. Is there any other choice in the literature for this distribution, or did you get to make tests with another distribution?
Actually, no. We have just used this type of distribution. Yeah.
Thanks. And what do you see as the next steps of your research?
I think that the next step is to work on those causes of the failure. As we can saw in this study, they have a lot of problem with maintenance in this company. It's a company from the food sector, and they actually don't have a job related to reliability in their lines. So I think that the next steps is to work on those main causes of the failures, like the welding of the packages and some other causes. Okay.
Okay. Thank you, André, for your presentation and answers.
Okay. Okay. Thank you.
So now we'll be making a brief break, and we come back.
E agora que estou no mercado, o que eu posso fazer para melhorar minhas relações dentro da engenharia? A ABCM, em parceria com professores e profissionais da indústria, procura mostrar ao jovem engenheiro as vantagens de se afiliar e de caminhar juntos dentro da profissão. Com amplas oportunidades estabelecendo contatos e novas relações, as associações podem ajudar a sua navegação no mundo da engenharia.
E vocês podem perguntar, eu que não estou num grande centro, não estudo numa grande universidade, como é que eu me insiro nisso tudo? Eu acho que essa transformação digital está viabilizando essa proximidade. E as associações estão se modificando para isso.
Faça network na universidade, faça amizade e faça parte das associações, como é, por exemplo, a ABCM.
A ABCM, Associação Brasileira de Engenharia e Ciências Mecânicas, é o principal agente promotor da engenharia e das ciências mecânicas no Brasil. Ela conta com cerca de 900 membros com formação em áreas das mais variadas, como engenharia mecânica, mecatrônica, civil, química, aeroespacial, naval, petróleo, materiais e metalurgia. E aí dá conta com pessoas formadas em física e matemática aplicada. Embora a maioria atue na área acadêmica, a associação procura estreitar cada vez mais a interação entre a universidade e centros de pesquisas e também com o meio industrial, especialmente com aqueles setores afeitos aos desafios tecnológicos atuais.
Dentro da BCM, o jovem profissional participa de eventos, expõe suas publicações e cria novos laços profissionais.
Para um jovem profissional, atuando em uma sociedade técnico-científica, é importantíssimo se manter atualizado. Neste contexto, a BCM disponibiliza material com o melhor do nosso conhecimento científico, por meio de publicações, livros, textos, monografias, revistas e análises de congresso. Organizamos diversos congressos de caráter regional, nacional e até mesmo internacional, nos quais os jovens profissionais podem divulgar resultados de seus trabalhos técnicos científicos e estabelecer networks com profissionais jovens e sêniores, relações que, uma vez estabelecidas, podem alavancar suas carreiras no presente e no futuro.
Precisamos dos estudantes, pessoas que estejam com novas ideias, estejam entusiasmadas para levar adiante, né, essa associação, né, estimulando as ciências mecânicas, a engenharia mecânica, né, apresentando suas novas propostas, né, e interagindo mais internacionalmente.
Nós jovens, nós que estamos na universidade ainda, temos um papel muito importante com a BCM, né? E ela tem muito a oferecer para a gente também, seja a possibilidade de ter bolsa de iniciação científica com alguns dos maiores pesquisadores da engenharia mecânica do nosso país, seja os descontos e facilidades oferecidos para você participar dos diversos congressos e eventos patrocinados pela BCM, seja por receber informativos e divulgações de oportunidades na área.
A BCM considera extremamente relevante o reconhecimento das pesquisas e trabalhos de graduação executados por nossos alunos. Razão para termos com frequência anual os prêmios Melhor Projeto de Formatura, Melhor Trabalho do CREEM, Melhor Dissertação no Mestrado, a BCM, é um prêmio em parceria com a Embraer, e Melhor Tese de Doutorado, também em parceria com a Embraer.
Então a BCM ela organiza alguns congressos no país, entre eles o COBEM, que é um ambiente bem legal, bem bacana para um jovem engenheiro, um cara que está fazendo seja um TCC ou mesmo um doutorado, para expor seu trabalho, conhecer outras pessoas e conhecer novas oportunidades de pesquisa ou mesmo de trabalho, né? A BCM tem alguns prêmios que eles dão para trabalho de conclusão, trabalho de pós-graduação. Foi assim que eu acabei conhecendo essa instituição, eu ganhei o prêmio de menção honrosa na categoria de melhor trabalho de doutorado.
E para todos aqueles que veem a pesquisa e o desenvolvimento científico uma profissão de vida, que mantenham a motivação, a empatia e a humildade e os princípios científicos, para obtermos um impacto concreto na sociedade e contribuirmos para que mais pessoas se beneficiem de uma educação de qualidade.
O prêmio realmente foi uma experiência muito marcante na minha vida, porque foi uma injeção de incentivo naquele momento para que eu continuasse buscando a melhoria do meu trabalho como pesquisadora e que eu acabei dando continuidade no mestrado. Então é muito legal a gente ver que existem instituições como a BCM que promovem esse tipo de ações, que incentivam a pesquisa científica, que incentivam o trabalho dos jovens profissionais, e ela faz isso de maneira singular, seja através das premiações, seja através dos eventos, através das bolsas de iniciação científica, que são muito importantes, da divulgação de oportunidades na área.
Assim, é algo bem interessante para se você conseguir inscrever o seu trabalho de conclusão de curso ou de pós-graduação nesse tipo de premiação, porque acaba dando uma visibilidade bastante grande para o trabalho, além de ser muito gratificante ganhar algo por um trabalho que a gente acaba colocando tanto esforço em si.
Nosso programa de bolsas de iniciação científica para alunos de graduação, no qual os 10 alunos de graduação de cursos nas áreas afeitas à engenharia mecânica são contemplados com bolsas de estudo com duração de 12 meses para o desenvolvimento de um projeto de pesquisa em universidades brasileiras, sob coordenação de um docente orientador.
Um dos eventos que eu participei como bolsista da ABCM foi o CREEM, com direito à isenção de taxa de inscrição, hospedagem e passagens aéreas pagas pela ABCM. Nessa oportunidade, além de apresentar meu trabalho, eu pude conhecer as mais diversas áreas da engenharia mecânica, abrir os meus horizontes e criar contatos, uma rede de networking com quem eu ainda mantenho contato até hoje. Antes do projeto eu não tinha nenhum contato com a academia, não sabia como escrever um artigo científico, e hoje em dia eu posso dizer que eu sou muito mais capaz de escrever meu próprio trabalho e apresentá-lo com confiança nos mais diversos eventos.
Para alunos de graduação, temos as escolas das quais participam alunos de graduação e pós-graduação. Nessas escolas buscamos disponibilizar conhecimento técnico e científico por meio de aulas e palestras proferidas por profissionais de destaque na área e no mundo, incluindo aqueles atuando na indústria e na academia. Entre as escolas destacam-se a de Turbulência, a primeira escola criada pela BCM, a escola de escoamento multifásicos e a escola de refrigeração.
Nós somos fortes, nós podemos, nós já mostramos que podemos nesses últimos 45 anos e agora cabe a vocês, jovens estudantes, continuar essa tarefa. O Brasil precisa de vocês, a engenharia mecânica precisa de vocês.
Participe de uma associação, construa seu network, identifique profissionais que possam compartilhar com você experiências positivas que vão ajudar na sua formação. A BCM está pronta, está esperando você. Você, jovem profissional, você, estudante, vem para a BCM.
Why don't we say that it's too late for us now? Why do we stay when I blame you for the things that weigh me down? 'Cause in the echo of your silence, I only hear what's best for me. Yeah, in the echo of your silence, I'm thinking more of her. She who wants to study your body, who gets the better version of you. I need the better truth. I need the better version of you. I need the better version of you. You talk about faith. Is it just something you say? Or is it the same with that girl you texted when I look away? 'Cause in the echo of your silence, I only hear what's best for me. Yeah, in the echo of your silence, I'm thinking more of her. She who wants to study your body.
So let's start our the main presentation of our symposium. This lecture will be given by Professor Daniel Straub. He is the responsible for the chair of engineering risk analysis in the Technical University of Munich. He's been working on risk analysis, sequential decision problems, and reliability analysis for the past 20 years. So he'll give the lecture with the title Decision Theoretic Global Sensitivity Analysis. So we thank you, Professor Straub, for accepting our invitation. And I pass the speech to him.
Thank you, Rafael. Thank you for inviting me and introducing me. I hope everyone can see my presentation well. And I apologize for not keeping the layout, but it was easier to stay in my own layout. This is a tower of our university that you see here. So I'm going to talk about decision theoretic global sensitivity analysis, and yeah, maybe that sounds still kind of not clear to you what that could be, but I hope in a few minutes you will understand what I mean by that. I'll start, let me see here, with just a general introduction. I mean, this is about uncertainty quantification. I guess you don't need that, but still it's good to be on the same page. So we use models in engineering, and of course these models can be different things. It can be parametric models, they can be numerical models, can be coupled models, more or less complex, but they all have inputs and outputs. And here in this context, I'm interested only in those inputs that are uncertain in some way and are modeled as random variables, both aleatoric and epistemic uncertainty. This model is just T of X here in this presentation. As I said, it can be simple or complex. And the output can be scalar, can be vector, but in this presentation I will also focus kind of on scalar outputs, but things can be generalized. Well, the input is, if these X are random variables, then the Y will also be random variables. And I guess that's clear. And we have different methods to propagate this uncertainty. Today I don't talk much about that, but what I have in mind are basically Monte Carlo-based methods, which use samples to propagate this uncertainty from X to Y. Simple example here, and I'm going to talk about that also later. Simple benchmark example for sensitivity problems in reliability. So here is a function. You see the function is nonlinear because it has in the X, the X are my random variables, and they include 4 random variables, M1 and 2, bending moments, axial force, and the resistance variable Y. And so this is nonlinear in both P and Y. And if I would ask you now, which of those 4 quantities is the most important one with respect to the output G, I guess you would not have an easy time to answer that question. Well, I wouldn't know. I mean, I've analyzed that, so I have some idea, but without doing some analysis, it's difficult to say. But in many contexts, that's exactly what we would like to know. So if you have uncertainty in these quantities, maybe you want to spend some time to get more information. But should you get more information on P, on M, on Y? Okay. So the first thing I'm telling my students to do in that situation is just to make a graphical representation if you can. So do some sampling, plot the samples of your inputs against the samples of the output, and you get some idea on how the output relates to the input and also on the scatter. So for a given value of M, the output is of course random because the 3 other random variables still are not fixed. So that's why we have this scatter. And the more distinct this relation between M1 or an input and the output is, probably the stronger the sensitivity of the output with respect to this particular input. So that's something we can do. But in many contexts, we would like to know or get some quantitative numbers, which are, allow us to rank things. So scatter plots are good, and you should always do that if you can, but you might want to use other things. And for example, popular are Sobol indices, also Shapley values. We heard about them already. But there are many other techniques and metrics you can use. So the question is how to pick them, which one to use, and how to interpret them. And I realized that this is something that people have not understood. Most people have not understood very well, also don't think about too often. So one typically knows a method, and then one uses this method for whatever. So, as I said, Sobol indices are popular, so people have learned how to calculate them, and then they are used for whatever. And well, in my experience, this is not the optimal thing to do, because each of these things have their, let's say, field of application, but there are also certain problems for which they are not very suitable. And if one doesn't really understand what they mean exactly, then it's hard to pick the right one. So I'm going to present another class of sensitivity measures that actually has the advantage, in my view, that it is very clear what they mean. They have a very clear understanding, and in practical problems that I have worked with, they're typically the quantities you actually want to know. So the question is, what do we really want to know from a sensitivity analysis? And I post another picture from from a real-life case study, or not case study, actually a real-life project, where there's a lot of uncertainty in the design of this structure. If you want to design the structure, there's a lot of uncertainties, for example, with respect to the environmental loads acting on this structure, current, waves. And the question is, okay, how important are these uncertainties? Do we need to care about them? So the question we would like to ask is, what is the effect that this uncertainty in a specific input has on the decision that we make in the end, or on the design that we come up with? And maybe even more specifically, how likely is it that additional information that we can collect, but which costs money, because it's not cheap to get this information, maybe we need more modeling. So how likely is it that this is going to change significantly my design, my decision? And that's a measure that I can relate to. And the decision maker, the people who pay money to do this thing, they can relate to it. Say, okay, why should I spend another $1 million to collect more data if it's not very likely that this data is going to change my design? Yeah. So this is the type of decisions that or the type of information I would actually like to have. And I'm now going to show you how we can construct sensitivity measures on this basis. So I'll start with a specific case, very basic case. So we consider that we have this model outcome Y. This represents a demand on the system. And then we want to make a decision on the design of the system, and we can choose a capacity, and that's A. When A is ultimately different from Y, we have a penalty or a loss, because we have either over-designed or under-designed. Here we assume that this loss is just a quadratic function of the difference between Y and A. So the loss function looks something like this. Okay? So there's no distinction whether we under-design or over-design. Either way, we have this quadratic loss function. So this depends on the distance from this. Now, under these conditions, one can easily show, and I have a paper where all this is and more is also explained, and I'll give the reference at the end if you're interested to download. But it's also intuitively, I guess, quite clear that maybe the optimal decision that you can do, the optimal design you can do, is to fix your design at the mean value of the predicted demand, so the expected value of Y. And if you do that, then the expected value of the loss is equal to the variance of Y. Okay, so the quadratic loss function leads to a loss on average, because your Y is not going to be exactly the mean value, and the expected value of this function clearly. You see here, we put this here, it gives me the variance. So now, what if we know the value of the input xi? So it's not written here, but remember, y is a function of my inputs x. And the fact that we have a variance in y reflects the fact that we have uncertainty in all these inputs. So now, what if we know one of the inputs? Hypothetically, if we knew one of the inputs, what would happen then? Well, the situation is similar as before, but now we would find a new optimal decision that's now still the expected value of y, but conditional on this, knowledge. So conditional on xi taking this value. And the corresponding expected loss is the conditional variance. And the good thing is that, generally, this variance cannot be larger than the original variance. So, and in general, it will be smaller. So learning about xi should reduce our variance in the prediction and should therefore reduce our loss that we have. We can make a better decision. But the difference here between these two quantities is the value we get when we learn about xi. Okay? We reduce our loss. And this difference in decision analysis is called a conditional value of partial perfect information. This is a very complicated name. Let's look at it, what it means. So conditional, because it's conditional on knowing xi. It's a value of information because it's a value that we get from knowing this. It's the value of information. And it's partial because we don't know everything. We know only something about xi. And it's partially perfect because we know xi perfectly. We assume we have a complete knowledge of xi. Yeah? We can also consider the case where we have partial knowledge of xi. But for here, we assume that we know perfectly xi. Well, that's great, but of course we do not know xi. So a priori, we actually do not know xi. So what do? Well, we say, let's take the expected value with respect to xi. So if we would learn about xi, what would be the value? And so we take the conditional value and we take the expected value with respect to xi. So we could learn that xi is 1, or we could learn that xi is 0. And we consider all these cases weighted, of course, with their probability density. And we get this so-called expected value now of partial perfect information. If we insert what we had before from this case, we end up, this is the variance of y minus this expected value, expectation of this conditional variance. And this can also be rewritten, one can show that this is the same as taking the variance over xi of the conditional mean of y given xi. And if you have some experience with sensitivity analysis, you recognize this probably, because if you normalize this quantity with the variance of y, if you take this normalization, you get the Sobol index, first order Sobol index. Okay? So this expected value of partial perfect information leads to the Sobol index in this special case. So we can say the other way around. We can say that the Sobol index is the expected value of partial perfect information, which is associated with knowing xi when we have a loss function that is quadratic. Okay. Now the good thing about this information, well, there's two good things about this. First of all, it actually allows us to get a better understanding what is the meaning of a Sobol index in the context of a decision. It also tells us that we can use this also when you have dependent inputs. Some people that work on Sobol indices say that it's only developed for independent inputs. And that has to do with the fact that Sobol index can be derived using variance decomposition. But when you think about it in the terms of the decision analysis or this value of information concept, it doesn't matter whether the inputs are dependent or independent. But it also tells us that if we have a completely different decision situation, Sobol index might not be the right quantity to use as a sensitivity metric. Okay? So now, what about other decision contexts? So if we don't have this quadratic loss function, for example, another real life problem that I was involved with, these power transmission towers. The challenge here was to understand and derive whether or not these towers are safe. Okay, if you have hundreds of thousands of them, and they had to be reassessed for safety. So the decision here was not something like, okay, we have to find an optimal design, but we have to decide whether or not they are safe. So it's more like a yes/no decision. We can also model that decision. Now the model is a bit different. So here we can think of it in terms of this decision tree. We have two options. We say it's safe enough, we do nothing. And then what can happen is that the structure is actually safe. And this, we model this by this kind of limit state function being larger than 0. Or we have a failure, and that means that this function is less than 0. If we have a failure, we have a cost of failure. If it's safe, we have no cost. Alternatively, we can decide to replace or strengthen. In this case, we can still have a failure, or we can have a safe structure. Yes, for now, in the future, well, now I'm saying that, okay, we neglect this possibility. We say the probability here is so small, we can neglect it. So no failure after repair. So we have a safe structure with the cost of CR, because we have to do a repair that costs something. The optimal decision is kind of trivial to find. It's replace if the probability of failure a priori, the probability of ending up here, is larger than this ratio of cost of repair to cost of failure. That's intuitively, I think, also clear. So now, what is here the value of knowing xi? We basically would repeat this analysis for different values of xi, calculate the probability of the reliability, we calculate the probability of failure for given values of xi. And if it turns out that this value is conditional value is larger than this, we should replace, otherwise do nothing. So if the new decision is the same as the previous decision, a priori decision, then there is no value because we don't change the decision. So knowing this, having this additional information will still lead to the same decision. So there is no benefit from an engineering point of view. However, if the decision changes by that, then we have a value. And this is now, again, this conditional value of partial perfect information, which is just the difference between the cost of repair and the risk, the cost of failure times the probability of failure. Okay, and again, we can take this expected value with respect to xi because we do not actually know xi, so we have to do an integration. Keep in mind that this is a one-dimensional integration, so that can be solved numerically if you know this function. And we need this function, and to know this function, we need to know the probability of failure in function of xi, conditional on xi, and that's something that we would need to compute efficiently if we want to be able to evaluate these sensitivity measures in a practical application. Well, before I show how to do this efficiently in 2 slides, I will just summarize here up to now. This expected value of partial perfect information is a sensitivity measure that was actually proposed late 1990s for the first time. It measures the effect of the uncertainty on the decisions. So it really accounts for what do we do with this model? How is the information used? It depends not only on the engineering model, but also on the decision. So, which is a good thing, but it requires you to specify what is the decision. Another good thing is that it applies to dependent inputs. So whether it's dependent or independent inputs doesn't matter. And as I said already, its computation requires the conditional expected value of this function. Before I said we need the conditional probability of failure, but the probability of failure is also an expectation. Okay, so that's why this is the more generally we can think of. We have to calculate some expected value for given value of xi for all possible values of xi. Okay, so how are we going to do that in the case of the probability of failure? Well, actually, there's a very basic idea that one can use, and thinking now of sampling-based approaches. Okay, in the paper we describe also other approaches, but in the sampling-based approach, well, what we end up if we use Monte Carlo, or in this case, importance sampling for computing probability of failure, you end up with failure samples. So the red here is the failure domain, and the green are my samples from an importance sampling density, and the green dots in the red area are the failure samples. This is the original distribution, by the way. We still are far away from the mean or mode of the distribution. So we have these samples, and we can use those to construct using a kernel density estimator, a conditional density of each input, in this case M1, given that we have a failure. So you take the marginal distribution of these samples that are in the failure domain, and you get this black line. And now you can actually use a simple trick using the rule of Bayes by taking the ratio of this distribution to the original distribution, multiplying with the probability of failure. What we get is this conditional probability of failure. And the nice thing is that we do not need to run our model again. We have already these samples from our reliability analysis, so we can just use these samples to construct the black density and then evaluate this analytically. So no additional model runs, basically for free. And once we have that, so this is basically shown above. So we have for another case here for a resistance variable. So this is the a priori distribution. In this case, the failure samples are to the left because we have smaller resistances lead to failure more likely. So we take this ratio, and this is the resulting probability of failure, conditional probability of failure for given value of R. And now, what is important here is that we can put here a threshold. And this threshold is remember, this cost of repair to the cost of failure. So above here, you should do a repair. Below here, you should do nothing. And we can find now what is the value of R at which the decision changes. So for these values of R observed, we should do a repair. For this, we should do no repair. And so we find this threshold, and this allows us to compute the conditional value of partial perfect information. In this example, the a priori decision is to do nothing. So if we have observed a value of R that is larger, we still do nothing, so there's no value, zero value. But if the value of R observed is larger than, sorry, is below the threshold, we will change our decision. And the value of changing the decision increases with smaller value of R, because in this case, the probability of failure, the conditional probability of failure becomes higher and higher, the risk becomes higher and higher. And a priori, we would have made the wrong decision. Okay? This is the conditional value. Then we can do the integration, and we calculate in this case that this expected value of partial perfect information is 3.5 million. Now we can do that for all the inputs, compare these numbers, and this is our sensitivity measure. Both relative, but also absolute, because we tell the decision maker, okay, potentially there's a value of 3.5 million to knowing this value better. So maybe you better invest 100,000 euros to learn more about this quantity. So for practical decision making, we have found this to be an extremely useful quantity. Good. I think I'm okay in time, so I can show you the numerical examples. Today are very fast, so don't worry. I will just need 3 more minutes, I think. So I will just show briefly this example that I showed you before. So what is now the important quantity here? The probability of failure we would evaluate first using some sampling-based approach in the order of 10 to the minus 2. Yeah? Just keep that in mind. And now I'm going to show you the resulting sensitivity measures that I computed exactly using the method I presented. So we use the failure samples, construct the density, calculate the conditional probability of failure, calculate the conditional value of partial perfect information, and do a simple one-dimensional integral to compute the expected value. And if you do that, and here I have the numbers normalized so that we can compare them, okay? So the expected value is normalized to always, this is the percentage contribution. So I have sensitivity measures with this EVPPI normalized in 3 different cases, plus also from 2 existing reliability sensitivity metrics from the form alpha values, and this is for dependent inputs, because these inputs are actually dependent. These are taken from a paper, you see. So anyway, these inputs here, you see, well, these inputs, these sensitivity measures are pretty consistent here. Now, when we look at the EVPPIs, we see they are actually changing. They are changing with what? They are changing with the threshold that we assume here. So this ratio of cost of repair to cost of failure. So this is the case where actually it's cheap to repair. In this case, the a priori decision is to repair. And in this case here, it's expensive to repair, and the a priori decision would be to not repair. So the change of the decision would be towards maybe, yeah, if we find an extreme case, we would still repair. Here, if we find an extreme case, we would not repair. Here, we are very close to the prior probability of failure. So here we could move easily. So here we have the highest probability of a change in the decision. And we see also that here, the sensitivity measures of all 4 inputs are very similar. Because we are so close to the threshold, it means that learning about any of these quantities is likely to change the decision. Okay? In this case, that's not the case. Here, only the most important quantities are more likely to change the decision. This case is somewhat similar to the form results. This case is quite different from the form results, and this case is even more different. So here, this quantity, which is the second most important quantity, is suddenly the least important quantity, because on this side of the tail, it's not very likely that P is going to change the decision. Yeah? So you see that the sensitivity actually changes depending on what is the context in which we are in. Yeah? And for the practical purposes, where we actually almost always have a decision, this is a benefit. It helps us to understand the sensitivities for this particular decision. Okay, so here's another example of this displayed in the paper. This is just to show that, okay, we can also do this with numerical models, of course. So this is a geotechnical problem where we have this monopile foundation. We have a random field here. We have a complex, slightly more complex uncertainty model. So H is a random variable whose parameters themselves are random variables. Uncertainty in the annual maximum statistics. And we can, of course, do the same thing, same procedure, nothing different. Here we use surface simulation. I also consider here 2 different decision cases. One is the failure case, and one is the design case, where I optimize the design. This is more close to the so-called case. And again, we have different sensitivities. Okay, the time is over, so I'm not going to explain the differences here. But depending on what you're doing, so depending on what your decision case is, you get different sensitivities. And you can read it in the paper if you are interested in more detail. So just to take home message, to summarize, this expected value of partial perfect information, it can provide a decision-oriented sensitivity measure with a clear interpretation in respect to a specific decision. It can be computed, at least in some cases, like I showed, as a side product of the uncertainty analysis or reliability analysis without running the model again. So it's kind of cheap or almost for free. But this is not the case in all decision contexts, okay? So for some decision contexts, actually, well, at least up to now, we have not found a way to avoid additional model rounds. So that depends a bit. What is your decision context? And so, yeah, clearly this EVPPI does depend on the decision case. So if you are running, maybe in research, sometimes it's the case that we do not know what is the decision that's taken afterwards. And in this case, it's maybe a bit difficult to specify a decision case. But in practical applications, typically you always know what the model is used for. And maybe the model is also used for different things, but then you can consider these different kind of decision cases. In either way, it helps to understand what one actually does with the sensitivity measured. And as I said, also Sobol index and other sensitivity measures are actually special cases of this expected value of partial perfect information. Good. This is the paper. I can also put this link in the chat if you want. Yeah, that's it from my side. Thanks for listening. And I used my time, but maybe there's still time for one or two questions.
Thank you. Thanks for your talk, Professor Straub. We have some questions here from the chat. The first here is a comment from Professor Hito. He thanks you for the talk and writes, it's reassuring to know that Sobol indices are a good choice for sensitivity analysis. On the other hand, it's interesting to see that for decision making, for instance, probability failure, a different perspective might be needed. And then a question from Professor Américo. Could you comment the differences of computing sensibility indices with and without no correlations between parameters?
Yes. So in this context here, there's no difference in computing. This case also has correlation, but maybe I'll show first this case. I use this case. So this case has correlation. Well, the resistance is not correlated, but the free load quantities are correlated. Now, you do your reliability analysis, your uncertainty analysis. Let's assume here in this case, that we do it with sampling-based approaches. So we end up with our failure samples. And we can just use whether they are coming from a correlated or uncorrelated distributions. In the end, does not matter. We marginally look at these distributions, these conditional distributions, and we do the procedure. There is of course a meaning to it when there is correlation. And here, the meaning is that when we observe, let's say we want to know the sensitivity of M1. Now, when we observe M1, because of the correlation, we also learn something about M2, and we learn something about P. So, in the end, the importance measure we get, this expected value of partial perfect information, accounts for, on the one hand, the information we get on M1 and how that changes the failure probability. But it also accounts for the fact that we indirectly learn something about M2 and P. So let's assume I have another quantity, let's say a fifth random variable that does not appear in the model, actually, but is correlated with these other quantities. Then that quantity would also have an importance. It's purely because of correlation. Because learning that quantity means that we learn something about these other quantities. But that's also the situation in the real life example. So if I have a real life project and I have another quantity that I could easily observe, and this quantity is correlated with another quantity that enters the model, I might want to think of learning this quantity because it would allow me to potentially reduce my uncertainty on quantities that appear in the function. Yeah. Okay, it was a bit a longer explanation, and I hope it's clear. So there is a meaning to this, and of course, if you say that you want to know only the sensitivity, or you want to know only the influence that comes not from the correlation but from directly into the function, then that would not work in this like this. But when you think of the decision, then the correlation always matters. So.
Okay, thank you, Professor Straub, for your presentation, for answering the questions. So here we finish our second session on uncertainty quantification. We have a short break, and then we retake the presentations at 11:15. So thank you all for coming, and see you in some minutes.
Thank you all. Okay.
So good morning, all. Welcome to the last section of the morning. My name is Adriano Fabro from the University of Brasilia. This presentation, this section has two presentations. The first by Victor Mardonet from the State University of Rio de Janeiro, and the last one from Professor Tiago Rito from the Federal University of Rio de Janeiro. So the first presentation will start now with the video.
Good morning to everyone. The title of the work is Parametric Probabilistic Model for Predicting Creepy Remaining Useful Life. The work's advisor were the Professor Américo Cunha and the Dr. Carlos Frederico. This presentation is divided into introduction, probabilistic framework, and final remarks. I would like to start this presentation with the following question. How much does humanity depend on high temperature to generate energy? Much is said about the transition of the global energy matrix to renewable energy sources, but we are still going to depend a lot on high temperature to produce energy, as you can see in the graph. By 2050, more than 50% of the world's energy matrix will still produce energy through high temperature applications. The global context today is a context of growing demand for energy. Modern society consumes more and more energy, and productivity must increase to be able to meet this demand. Analyzing the Brazilian case, I took this graph from EPE, which shows the forecast demand for electricity here in the country until 2050. And as you can see, that this demand is expected to triple by 2050. So, to increase energy productivity and meet growing demand, it's necessary to increase the efficiency of thermal processes. This is only possible if we increase the temperature at which this process occurs. However, the materials available in the industry today are not able to withstand higher temperatures and are the limiting factor. So in this sense, it's essential that we have a good understanding of the process that degrades materials at high temperature, so that we can elevate temperature and efficiency. One of the main phenomena that degrades materials at high temperature is creep. Creep is characterized by a slow and progressive plastic deformation, and it's a phenomenon that depends on time, temperature, and mechanical stress. Creep is mainly studied through creep tests. However, most materials are designed to operate for more than 10 years, and it's absolutely impractical to conduct creep tests for 10 years. Therefore, it's necessary to use some extrapolation methods that predicts the life of a material in creep. And the most traditional method used is the Larson-Miller method. Here you can see also the equation of this method. And what happened is that historically, the experimental data produced by creep tests presents a large experimental dispersion, and the life prediction methods traditionally used are mostly deterministic. That is, they are not able to account for this dispersion in the experimental data. To illustrate this, I made this graph of the Larson-Miller parameter against the mechanical stress. The experimental data was taken from NIMS, the National Institute for Material Science in Japan. It's an institute that has one of the most reliable creep databases in the world, and the material selected was the chromomolybdenum vanadium. In this sense, the purpose of the article is identify parameters irrelevant to the parametric creeping model through a global sensitivity analysis based on Sobol indices, and propose a probabilistic version for parametric creepy life prediction models. So this was the probabilistic framework used in the work, and it's divided into 5 steps. The first is statistical model construction, then sensitivity analysis, then uncertainty modeling, then uncertainty propagation, and finally model certification. First, the Windsor-Rising technique was used to treat the experimental data and eliminate possible spurious data. Data in blue is data processed, and data in red is unprocessed. To determine the relationship between the Larson-Miller parameter and the mechanical stress, sequential threshold least square was used together with cross-validation. The sequential threshold least square is a type of sparse regression and was used to avoid presumptions in determining the polynomial relationship. The cross-validation was used to access the accuracy of the established relationship, and the root mean square error was used to rank the polynomials. In the final of these processes, this was the selected polynomial. As you can see, it's a linear polynomial. So the parameter and the mechanical stress has a linear relationship. In the global sensitivity analysis, the indices were calculated using 2 different methods: the Monte Carlo method and the polynomial causa expansion method. The Monte Carlo method was used as a reference, and the polynomial causa expansion was used because it's computationally cheap and because it prevents cancellation errors in the higher order indices. So this is the first order Sobol indices, and we can observe that they converged for both methods, and we could also see that the isolated effect of each parameter on the response is small, and that the interaction effect between the parameters are more relevant than the isolated effect. So to corroborate this fact, we can see in the total order indices, which count the sum of all interaction effects of each parameter, it shows how the interaction effects are in fact relevant to the response. And also we can see that the parameter A1 is irrelevant to the response and could be eliminated from the subsequent analysis of the framework. In the uncertainty modeling step, the input parameter estimator are asymptotically Gaussian correlated by the central limit theorem. Then a multivariate Gaussian distribution was used to model the uncertainties. And this was the equation of the multivariate Gaussian distribution. In the stage of propagation of uncertainties, the Cholesky decomposition was used to do it to the correlation between the estimators, and 10,000 samples of the rupture time were produced for each selected operation conditions. These were the selected operating conditions. The objective was to simulate different operating conditions of real plants. And these were the histograms obtained for the rupture time for the 4 selected operating conditions, And as we can see, the rupture time has exponential distribution, corroborating the large dispersion present in the experimental data. We can also see that the 95% confidence interval was able to cover the experimental value of the rupture time for all experimental conditions. And here are some statistics inferred from the generated samples. We can observe the notorious experimental dispersion from the coefficients of variation. We can also observe that the variation was slightly smaller under the lower temperature condition, and that the cryptic rupture time strongly depends on the temperature. The final remarks that we can extract from the work are that the isolated effects of the input parameters are irrelevant, and the interaction effects between them is relevant. The coefficients A1 for the Larson Miller model do not significantly affect the response, and the rupture time has an exponential distribution. Thank you.
Thank you very much, Victor. We don't have any questions from the chat right now so far, but I do have one or two questions actually. I'm not very familiar with this kind of creep phenomena, but I was very curious about your sequential least square thresholding approach for fitting the best polynomial to your Larson-Miller model. It's curious to me that you actually have got the linear polynomial as the best fit using the sequential least threshold, which I understand is a kind of sparse regression type of scheme. Can you comment on that? Because I would expect something more complex than a linear polynomial to fit that data. Victor. Can you hear me?
Yes, I can hear you, okay. Adriano, but still hearing the presentation. I'm trying to fix this.
Do you have your the conference link open as well?
Now it's okay. It's okay.
It's okay.
Sorry.
Did you hear my question, or do I have to?
No, I didn't hear your question.
Okay. So I'm not. I was saying that I'm not very familiar with this kind of with creep modeling or this kind of phenomena in general. But I was very curious about your. I'm very curious about your sequential least square threshold approach for modeling the Larson-Miller relation, and which you end up, which you, as far as I understand, you use a kind of a sparse regression scheme. And then you've shown that the best fit for that using the scheme is the linear polynomial. It's a linear polynomial in general.
Yes.
But it seems to me from the data that you have presented in the paper that perhaps a more higher order polynomial would be the best fit, or I don't know. Can you comment on that a little bit on this process?
Yes. When you were constructing the statistical model, we have two options, observing the data. it's possible to be a linear model or a quadratic model. So, but with the cross validation and the sparse regression method that we use, it confirmed for us that was a linear polynomial that modeled this relation. But we were in doubt about the linear polynomial or the quadratic polynomial.
Yeah, perhaps the choice of the norm, which is like a L1 norm kind of thing, rather than L2 typical, when you do a minimal square kind of fit, kind of led to that decision, I guess, perhaps. But I mean, that's very interesting as well. So we still don't have any questions from the chats, but I have a second question actually. As far as understood from the work, you're trying to put forward a more general framework for probabilistic model this kind of phenomena. But you are using this simple analytical model for CRIP, which is this Larson-Miller.
Yeah.
I understand that you, at some point, you're going to use more complex modeling for that. Can you say how do you plan to do that? What changes on your does it affect how does it affect your framework, or what do you expect from that?
Yes, actually, this framework is expected to be a generally framework to be used in other applications and in high temperatures. But what happens that the research community which works with this kind of things is not much familiar with statistical techniques, with uncertain quantification techniques. So the intention is to provide to generalize this methodology, this application for the community, you know. It's a further step. It's not my pretension to make a general methodology for use in high temperature applications. You know, it's a first step to other works, other research to get this work, understand these techniques, understand the power of these techniques, and get this to make a further step, you know. And that's it. I guess I answer your question.
Yes, yes. I have a comment from Professor Americo da Cunha. He's saying that the sequential threshold least square approach tries to obtain the best polynomial with the maximum of zero coefficients. He started with a high order polynomial, then the sequential threshold least square algorithm showed that a line provides the best parsimonious fit, while the traditional least square gives a high order polynomial with many small coefficients. So I understand that the main benefits that you have less coefficients to fit, less coefficients to take into account in general, and thus the simpler your probabilistic model as well. So thanks, Americo, for that. Do we have any more questions or any more? No? If not, so I'm gonna, and thank you, Victor, for your presentation. Okay. We're actually a bit off the schedule from which I have here. So I suppose the last presentation was supposed to start 11:30. So we're 15 minutes past that. So we can move on to the final presentation, I suppose. Given by Professor Thiago Brito from Federal University of Rio de Janeiro. So please, if you can start the video.
So my name is Thiago. I'll present the paper entitled Sensitivity Analysis of Dispersional Vibration through a Strain Using Suball Indices. This work was done by Edson Fabian and myself. This is the outline of the presentation. Just talk a little bit about my research interest. These are the areas: dynamics, control, parameter estimation, certain quantification, and machine learning, computational mechanics. And the applications vary, but mainly mechanical, outdoor dynamics, wind turbines, geostring dynamics, and recently a little bit of Hall dynamics with my colleague from FRG, and COVID dynamics with another colleague from the State University of Rio. Currently, I'm in Bristol and a part of this digital twin project. This is the problem that we are worried about. I've done a lot of work in this area. On the left, you can see the sketch of TrueString, which is a lambda column with many interactions. And on the right, you can see that we're able to produce models that are consistent with the field data. And we're considering stochastic models to represent this fluctuation of the experimental response. For this work, we will consider a single degree of freedom system with only torsional dynamics. So we have on the left linear system, but it becomes nonlinear when you consider the nonlinear interaction, bit-rock interaction on the right. And you can see the formulation of the bit-rock interaction, which is a regularized friction model. Our goal is the sensitivity analysis. So the output that we are interested in is magnitude of torsional oscillations, and the parameters that we are considering uncertain. So we'll propose a realistic model for that. Are these parameters, which include the bit-rock interaction parameters and also the operational parameters, which are omega and W. For these, we're using the Sabal indices, so I will not be able to go through the details, but there's the first order index and also the total Sabal index that considers the first and higher order effects. So there are many ways to estimate this index. In our case, we use the UQLab. We are proposing, since we are considering different operational parameters, we are considering 2D map, which I'll show in the sequence. We propose this normalization, which takes into account the variance, maximal variance of the whole map. And that's how we normalize the first order and the total index. It's something that we propose in this paper. To have an idea, I show here the severity of torsional vibration, the output that we're interested, which is represented by different colors. So for different omega and W, omega and W, you have a different value for this output. And we see that there's a jump. This is 0 oscillations in dark blue region, and then it jumps to some value greater than 1. So we imagine that in this interface we have more sensitivity. So let's see the results. Considering these 3 parameters as random variables, this is the first order Sabal indices. So we can see that exactly in the interface, we see more fluctuations, or more sensitivity in this part. And also on the top, the left top part that is considered here. And alpha 1 is the most sensitive when you consider these 3 parameters. This is the total index. So we have similar results, but now it's even more clear that we have this huge uncertainty interface that separate the system without torsional oscillations and the system depending on the configuration of the parameters that has more oscillations. We do the same thing for the 2 operational parameters, omega and W. and we have different graphs. So the sensitivity is not so big, but we see that it's also concentrated in this limit region that separates high oscillations and low oscillations. So the same thing for the total Sobol index. And finally, I'm just showing here, when we consider all the parameters uncertain, we see clearly that that alpha 1 and mu are the two parameters that are more responsible for the variation in the output for this specific system with the specific modeling that we are considering. So you can see this is the total Sobol index. This is the influence of alpha 1, this is the influence of mu, and the others, they don't produce a high oscillation or high sensitivity as these two factors. And now that we quantify that, we know exactly how far we have to go if you want a safe operation. So we cannot consider something that is close to the region, and now we know how much further we have to go to the right bottom to get a safe system. So that's it. To summarize, we're proposing here a sensitivity analysis based on Sobol indices to evaluate influence of rotational speed and bit-rock interaction parameters on the response of the drill string. And we are considering a map for that and a specific normalization. The application was in this simple 1 degree of freedom torsional system, but the idea can be applied for different systems and also to a more complex drill string system. Next steps is to consider other deterministic models and stochastic models and see how sensitive is different responses to different probabilistic models. I'd like to acknowledge financial support of the Brazilian agencies and also the Federal University of Rio. And thank you.
Okay, thank you for the presentation, a very nice presentation. I don't see any questions here in the chat. So if you have any questions, you can make it. I have one question, but it's more general in terms of what you've shown in the first slide about your digital twin project in terms of this kind of bit-rock interaction. So you understand you're applying this concept of digital twin or for bit-rock for well production as well, or is it more like and understood it's more related to wind farms rather than this kind of engineering system? How do you do that, or can you comment a little bit on that?
Yeah, thank you. It's just a comment, very disturbing to watch your own presentation.
Yeah.
I didn't like the experience, but yeah, this is just one little part of a bigger project did by a colleague, actually a postdoc student, not student, a postdoc, not the whole thing that he did. Now in the digital twin, we're doing many things, but I'll just talk about one. So one thing that we wish to do is to collect data and try, for instance, to fit the best model, but we don't know which bit-rock interaction model is the best. So while drilling the real structure, we want to select the best model and then try to make a decision, at least try to predict what's going to happen. But if the data change because the bit-rock interaction changes, you can just update it and have a better model to make a decision. So that's one thing that we did, and we are using ABC, which is a Bayesian approach for trying to, I think maybe you saw this presentation, but a different one. So they use ABC for parameter calibration and also use reinforcement learning to help to select models. So that's the idea. And another thing, just one more comment, I'm doing with Professor Americo. We are working in a COVID dynamic model. And what we do, we use these Sabal indices as a first stage of our methodology, such that we know which parameters are more sensitive, such that we can, in the second step, solve a calibration problem, inverse problem for the specific sensitive parameters.
So thank you for that. I mean, the idea is, if you're looking for a digital twin approach, is it like that you perhaps you're going to be using this Sobol index kind of calculation sort of online while you're deciding to which is the best model, which might change depending on the conditions of your operation, as far as you understand, or no?
No, the idea for the sensitivity analysis is, let's say, a first step before putting the digital twin to work.
Okay.
So as a first step, you understand a little bit about your model, and then you just go and you keep calibrating and updating your model with this, let's say, previous study concerning sensitivity. So it can also be done, but it's costly to do to compute it online. So we want something faster, just to, okay, I know that something changed, I want to make a better decision, and beforehand we need to have an idea about the model and the sensitivity of the response with respect to some parameters. So that's I think it's not directly correct. This work was done before I came to England, so it's just a first step for the digital twin.
Okay. Thank you very much. We have one question from Professor Americo da Cunha. So he's asking, Tiago, did you investigate how the maps pattern changes if you use different prior distributions for the parameters?
So I didn't do this, and it's very important. Not only, I mean, the prior itself, but also what's the support of the distribution. So what's the standard deviation of the distribution? So he's right. Depending on the model, I have different indices. This specific investigation, what we had a little small problem, because since we are doing a 2D map, for each point, I have a different sensitivity. So the idea was to normalize with the maximum sensitivity such that we have some comparison. So that's what we did. But so we answered again, we did not try different distributions or different supports, but they are important.
Okay, so thank you very much, Tiago, for the presentation, your discussion. So it's now almost 12, so I'm closing this section by the morning. And as far as I understand, I'm also closing the sections on uncertainty quantification and stochastic modeling. So I would like to thank everybody who's taken part on this section, either by participating, just watching, following, or taking part in that. So yes, thank you very much, and see you.
Thank you.
Thank you. Fechou. Acho que foi legal.